we're going to be looking at one standard analytical technique in solving Riccati differential equations. These equations are of the general form dy dx is equal to p of x plus q of x times y plus r of x times y squared. It looks like a second degree polynomial or a quadratic equation because we have this y plus y squared. Obviously, nevertheless, we have a differential equation. And it's also important, I believe, to notice at least a couple of things. For example, if r happens to be 0, then what does that entail? Well, that goes away because r is 0. And if you look, we then have a linear differential equation. Also, if p happens to be 0, what does that entail? Well, that goes away, and if you look even more closely, you'll then see we have a Bernoulli differential equation. So now the question is, how the heck do you solve a Riccati differential equation? Several textbooks give the following technique. It's an analytical technique and depends upon knowing ahead of time a particular solution, or at least guessing correctly a particular solution. So the first question is, how the heck do you get a particular solution? Now in a future video, perhaps I'll give some more hints in terms of finding particular solutions, but usually it's not super bad because oftentimes if you're given such an equation, a good guess for a particular solution is going to be something like y sub 1 is equal to a times x raised to the b power. Alternatively, it might look like y sub 1 is equal to a times e raised to the bx power. Usually those are good guesses. It'll be of that form. So if we have y sub 1 and y sub 1 is a particular solution, I'll just abbreviate solution, it turns out that the general solution is y is equal to y sub 1 plus u. Now this raises a couple of new questions. First off, what the heck is u? How do we find it? Second off, why does this technique even work? Now I suppose we could take a much more theoretical and abstract approach and prove this. But really, perhaps it will be almost sufficient, although not quite, just to show that if you do the appropriate substitution techniques, things will harmonize together, things will work out. Because essentially, once we do our substitution, that y is equal to y sub 1 plus u, we're going to get a Bernoulli differential equation. And we know how to solve a Bernoulli differential equation. And therefore, we know how to solve a Riccati equation. So let's just try that and see what happens. So if y is equal to y sub 1 plus u, here we should first think about its derivative. So that would just be dy dx is equal to dy sub 1 dx plus du dx. Great. And now we can make our appropriate substitution. Because we know dy dx and we're saying it is this, we also know this y and this y. That happens to be that. So now we can do our substitutions. On the left-hand side, we have dy dx, and we're saying that is the same as, so to speak, dy sub 1 dx plus du dx. On the right-hand side, we have p of x. P is a function of x. To shorten this, I'm just going to drop that x. We know that p is a function of x, so we'll just say p plus q times y, which happens to be y sub 1 plus u. We just substituted that in there, plus r times the quantity y sub 1 plus u squared. Great. And now let's just work more on that right-hand side. We have p plus q y sub 1 plus qu plus r y sub 1 squared plus 2 r y sub 1 u plus r u squared. Now if you look closely, it's a little bit subtle to be sure. Things will drop out very nicely. We can simplify this. It looks like a mess, but it's really based on, first off, the knowledge. We know from the outset that dy dx is equal to this right-hand side. And that actually appears right in our equation. In other words, we know what dy sub 1 dx is based on our equation here from the outset. And so, dy sub 1 dx is equal to p plus qy sub 1 plus r y sub 1 squared. And because of that, we can drop that out. We can simplify it, and the equality still holds. And so, we now have du dx is equal to qu plus 2 ry sub 1u plus ru squared, which is great because if you look closely, in fact, this here is a Bernoulli differential equation. In general, a Bernoulli differential equation is of the form dy dx plus p of x times y is equal to q of x times y raised to the n power. So we can take this equation and algebraically manipulate it, so to speak, to put it more of this form, in the sense of making it more explicitly of that form. So let's do that. So first I'm going to do a little factoring. So we'll say du dx is equal to u parentheses q plus 2 ry sub 1 close parentheses plus ru squared, and then we can get du dx minus u parentheses q plus 2 ry sub 1 close parentheses is equal to ru squared. And this now definitely looks like a Bernoulli equation, because after all it is a Bernoulli equation. And we can solve that. We know how to solve that, so let's do it. We would usually do a u substitution here, but the letter u is already used, so we'll use w instead. But first, I'm going to work on this equation a little bit more. So we'll take du dx minus u parentheses q plus 2 ry sub 1 is equal to ru squared. We'll take that, multiply the entire equation by u to the minus 2 power. So now we have du dx u to the minus 2 minus u to the minus 1 parentheses q plus 2 ry sub 1 is equal to r. Great. And we'll stipulate that w is equal to u to the minus 1 power. We'll take its derivative. dw dx is equal to minus u to the minus 2 power du dx. And from this, it follows that du dx is equal to minus u squared dw dx. Now we can do our appropriate substitutions. du dx is just this. U to the minus 1 is that w. So now we have, for du dx, we have minus u squared dw dx, u to the minus 2 power minus w, parentheses q plus 2 y sub 1, and that's equal to r. We could simplify, so we have minus dw dx minus w parentheses q plus 2 y sub 1 is equal to r. And I'm just going to multiply it by a minus 1. So we have dw dx plus w times the quantity q plus 2 y sub 1 is equal to minus r. And definitely, we now have a linear differential equation. So in general, that's of the form dy dx plus p of x times y is equal to q of x. And we have that. We also know how to solve that, so let's just go for it. Let's go for it. All right. So with a linear equation, we could do our integrating technique, our integrating factor technique. So mu is going to equal to e raised to the indefinite integral of q plus 2 y sub 1 dx. We will multiply the entire expression by mu. And then, because of this integrating factor technique, we know the left-hand side is equivalent, of course, to the derivative of the product of W mu. We can anti-differentiate. So we get W mu is equal to the indefinite integral minus R mu dx. We know that, for example, W is equal to u to the minus 1. So we could say we have mu over u on the left-hand side. And then we can keep on going to solve u. So u, not mu, excuse me, u would equal mu over the indefinite integral of minus R mu dx. And so we have a general solution that y is equal to y sub 1 plus mu over this indefinite interval. Not bad. But how about doing an example and following the same exact kind of pattern to put some meat on this proof? Because it's pretty general and it's pretty abstract in its own way. So if we have something like this. So let's say we have dy dx is equal to minus parentheses 1 plus x squared minus parentheses 2x plus 1y minus y squared. And we're going to be given from the outset that a particular solution is y is equal to minus x. So our general solution is going to be something like y is equal to minus x plus u. We're going to need to figure out what u is. So first, from our general solution, let's take the derivative. So now we have dy dx is equal to minus 1 plus du dx. Great. And then we can do our substitutions, just like last time. We have this dy dx, that's what that is, and we have this y here, and we know what that is. Great. So on the left-hand side, we have minus 1 plus du dx is equal to minus parentheses 1 plus x squared minus parentheses 2x plus 1, close parentheses. So y is minus x plus u minus parentheses minus x plus u, that quantity squared. So let's work on that right-hand side. Let's be careful here because there's lots of negatives and so forth. So we have minus 1 minus x squared minus, let's multiply this out, and let's be careful. So we have minus 2x squared plus 2xu minus x plus u minus, let's square that. So this is x squared minus 2xu plus u squared. Great. And let's continue to work on that. So we have minus 1 minus x squared plus 2x squared minus 2xu plus x minus u minus x squared plus 2xu minus u squared. Great. And the left-hand side is just minus 1 plus du dx. And if we did things right, a lot of things should drop out. A lot of things should drop out and simplify. And they actually do simplify very nicely. It's a huge mess, but it's not bad. Because look, we have a minus 1 here. We have a minus 1 here. Well, that definitely can drop out, and the equality holds. Let's see. We have this minus x. We have this plus x. So that definitely goes away. We have a minus x squared. We have another minus x squared, so we have a minus 2x squared. But here we have a plus 2x squared, so those nicely go away. We have this minus 2xu, but here we have a plus 2xu, so that goes away. And so now we have du dx is equal to minus u squared. Great. And that's pretty nice. And we have a Bernoulli differential equation. So that's the form dy dx plus p of x times y is equal to q of x times y raised to the n power. That's great. So let's just rewrite this a little bit. We can get du dx plus u is equal to minus u squared. Great. And let's multiply all that by u to the minus 2 power. So now we have du dx u to the minus 2 plus u to the minus 1 is equal to minus 1. And then we'll do our substitution. We'll let w equal u to the minus 1, take its derivative. So dw dx is equal to minus u to the minus 2 power du dx. And from that, it follows that du dx is equal to minus u squared dw dx. We can make our appropriate substitutions. We have du dx, and we have a w. So now we have minus u squared dw dx, and that's multiplied by u to the minus 2 power, plus a w is equal to minus 1. We'll simplify. So now we have minus dw dx plus w is equal to minus 1. Let's just multiply everything by minus 1. So now we have dw dx minus w is equal to 1. And clearly that is a linear differential equation. Dy dx plus p of x times y is equal to q of x. So let's solve that. All right, so I got to think about the integrating factor, mu. So that's e raised to the, well, it'll just be a negative dx. So we have e to the minus x. Okay. So let's multiply everything by that integrating factor. We have dw dx times e to the minus x minus w times e to the minus x is equal to e to the minus x. This left-hand side is equivalent to the derivative of the product of w times e to the minus x. We can anti-differentiate, and so we get we to the minus x is equal to minus e to the minus x plus an arbitrary constant. We know that w is equal to 1 over u, so we'll just say 1 over u, and e to the minus x is the same thing as 1 over e to the x. And I'm just going to then times everything by e to the x. Why not? So we have 1 over u is equal to minus 1 plus c times e raised to the x power. And so we have u is equal to 1 over minus 1 plus c times e raised to the x power. So now we have our u. We also know our y sub 1, and so our general solution is y is equal to minus x plus 1 over minus 1 plus c times e raised to the x power. That is our solution. Not bad. And we follow the same pattern when we were doing our more generalized example, our very generalized example, to solve our Riccati equation. So we do our appropriate substitutions based on a particular solution, and then we get a Bernoulli equation. We just go from there. I hope this video has been somewhat helpful.